All right, Calculus 12, here we go. It is time for exponential and logarithmic derivatives. It's good times, and limits. So here's the deal. The topic, like I said, exponential, logarithmic, limits, and derivatives. This is 8.1 to 8.4, which is a weird mix because it's a mixture of pre-calc 12 prerequisites, limits, and derivatives. So it kind of has a whole whack of stuff linked together. So here's how I've broken it down as far as the pages go. I know it looks overwhelming at first, but just the way it goes. So within those 4 sections, a lot of it is pre-calc 12 review of all of your exponential and logarithmic processes that you learned in pre-calc 12, from graphing to solving exponential equations, logarithmic equations, all that kind of fun stuff. Then there's limits, and then there's derivatives. These two obviously are the calculus type questions we'll be going through, and I'll break this up into 2 videos, maybe 3 depending on timing, because this is a lot of stuff in this section. So here we go. Ultimate goal is, when dealing with this function b to the x, where b could be any base except 1, then and e to the x, log base b of x, and ln of x, or natural log of x. What are those derivatives? So our goal is to find out what are the derivatives of these 4 functions, just to add to our repertoire of derivative taking. And in order to find these derivatives, it's going to be a combination of prerequisite pre-calc 12 skills, exponential log skills, and then some limit knowledge. So we'll start there. We'll start with this guy, and then you'll see how it leads into this, interestingly enough. Here we go. So let's start with y equals b to the x. Just some random exponential growth or decay depending on the base right now. The only thing is we're just going to make a little stipulation here that b is not equal to 1, otherwise that's not growth or decay. So if that is the function we're dealing with, we don't know its derivative. If you were to go to Desmos and just take a wild crack at it, like someone might think, well, I can just use the power rule. You might think, well, you can just bring the x down, lower it by 1, and you might think that's the derivative. But if you actually go and graph this and graph its true derivative and this, not even close. So the power rule here is useless. As soon as the variable is in the exponent, power rule is out the window. So we have to go back to scratch. So back to scratch means we go back to derivatives with limits. There's our definition of the derivative of the limit. So now, upon going into here and going and plugging x plus h into that function, you get b to the x plus h minus b to the x over h. And then, as usual with limits, we have to figure out a way to evaluate this. And what someone figured out, because now we're dealing with exponents, you can write this: the addition of exponents is the same thing as multiplication of bases that are the same. So b to the x times b to the h is the same thing as b to the x plus h. You can factor out a b to the x, and when you factor out a b to the x, you get something interesting in the sense of, notice this is approaching, h is approaching 0. This b to the x has nothing to do with h at all. The original function had b to the x in it. So if I was to take the b to the x out front, which I can do because it's not influenced at all by this, someone had this interesting thought of, wouldn't it be interesting if the original function was b to the x? Wouldn't it be really cool if we could find out what base would make this part of it equal to 1, so the derivative of b to the x would be b to the x. So some people played with this. So then what you could do is you could go to a calculator, and you could just try, for example, let's try a base of 2. And if you go to your calculator and you type this in, so if I plug in a 2 for the base, I'd have 2 raised to a number close to 0. So let's go with 0.001, just make, I don't know what's close to 0. That number divided by 0.0001. And then you get this number of 0.9-ish. And it's like, okay, what number is that? That's weird. Okay, so it's not 1, but it's almost 1. So then someone thought, well, let me go and let's try base 3. So let's try base 3. Divide it by 0.0001, and then you get 1.09, so a little bit above 1. And then people started to play with this, and they found out, and we're looking for a number between 2 and 3 that makes this 1. What they found out, interestingly enough, is there's what we just talked about. What base makes this happen? That was the big question. And lo and behold, it works out to be this 2.71828. As you get closer and closer and closer, it actually gives you E. This is actually one way of approximating E, is using this particular limit. So this is a really cool fact. If the base is E, this part of the limit goes to 1, and the derivative of the original function e to the x is e to the x. So if you go to Desmos and graph e to the x, which remember e to the x is this look to it, it's exponential growth, the derivative of that function is itself. So that's a really cool fact, really neat thing. That's what makes e very special to the math world. And so out of that comes two facts. The derivative of e to the x is e to the x. And also this limit as h approaches 0 of e to the h minus 1 over h is 1. So there's a limit fact and a derivative fact that comes out of that. All right. Now, e comes in many places in math, but this is just one place that it kind of creeps up in. All right. So that being said, how do we then take derivatives of this function? So let's just practice a few just of that function there. So there's one fact for derivatives. So let's say now they throw this at you. They say take the derivative. And then they have something you're used to, and then they got this new function here. It is a times in here, so this is going to invoke the product rule. So the product rule, remember this is your first function, this is your second function. The derivative would be the first times the derivative of the second. Well, I'll write it out to start with. We're going to take the derivative of that plus the second function times the derivative of the second, which I know you can do in your sleep, but even this can be even better. The derivative of e to the x is e to the x. The derivative of x squared, as you know, is 2x. There's a good answer. What they might do, because there's an e to the x in common to both, they might factor out an e to the x. They might also factor out an x. So an answer could look like this. And there would be your derivative. Okay, what happens if you have not an x as the exponent? Well, similar, you got to think of this as this is the inside, if you want, of e to the x. It doesn't look like it. For example, if I give you like a function of tan, if I did tan of 2x, you can easily see that 2x is inside tan. It's just obvious. But if I give you e to the 2x, this 2x is inside the e to the x. So this is the inside of e to the x. So this here is a chain rule, where this is the inside and e to the x is the outside. So the derivative of e to the sine x would be, okay, so outer derivative, what's the outer derivative? The outer derivative of e to the x is e to the x, but evaluated at the inside. So it'll be e to the sine x times the derivative of the inside. And the derivative of sine would be cos. So you'd end up with, there would be your derivative. Cos x times e to the sine x. Okay? Hope that makes sense. Even before I do example number 3, let me do an example 2.5. Let's say you had y equals e to the 4x. The derivative of that would be, okay, outer function is e to the x, or e to the 4x. It would be outer function evaluated at the inside times the derivative of the inside. The inside is 4x, the derivative is 4. So your derivative would be 4 times e to the 4x. It's just the exponent doesn't look like an inside, and people get misled by that, but just the same meaning. Next guy, e to the negative 3x times cos of 2x. Okay, so what do I have? I have a product here. Product rule invokes first, so the derivative would be the first function times the derivative of the second. I'll write it out, although personally I've done this enough that I don't write that step out, but plus the second times the derivative of the first. Alright, so e to the negative 3x, what's the derivative of cos 2x? Well, that's a chain rule. So outer derivative, the derivative of cos, negative sign, inside stays the same, multiply by the inside, which is 2, plus cos 2x times this guy, which is another chain rule because that's the inside. Derivative of e to the x is e to the x evaluated at the inside times the derivative of the inside. Derivative of negative 3x is negative 3. And there'd be your awkward looking answer. I would probably do a lot of cleanup on this. I'd probably write it like this. I like to put my e to the x's last because it just looks a little bit easier on my head. And then I could factor out a negative. I could factor out an e to the negative x. That's it. And what am I left with? I'm left with 2 sine 2x plus 3 cos 2x. And so there's my derivative. Alright, 2 last examples here, and then I'll stop the video, and then we'll start up with the other derivatives that exist. So let's look at some limits real quick here. So remember, when you go back to limits, lots of ways to do limits. You could do it numerically, which is kind of a cheat way. I could plug really large numbers into here and kind of get an analysis of it. I could do it graphically. I might be able to do it algebraically. I would recommend, and also plugging in first. Let's think about it for a minute. If I was to plug in infinity into this, can I wrap my human head around this? E raised to a massive number, I kind of know that's infinity, okay? If I didn't understand that, another way of doing it would have been to graph e to the x. Remember, e to the x has this look to it, exponential growth. As x goes to infinity, the y value goes to infinity. Alright, here I could do this by plugging in. Now if I understand this, e to the negative infinity, I would personally write a negative exponent as 1 over. And then I would think about, oh, the bottom, e to the infinity is massive. What's 1 divided by a massive number? Oh, that's 0. Again, the other way would have been to look at the graph and say, as x goes to negative infinity, oh yeah, this approaches 0. The next one here, I'd be like, okay, how do I wrap my head around this guy? Well, I'm plugging in, first of all, I can't graph that with this weird exponent. That is not something I would want to entertain at the moment, unless I really had to. So I don't have the graph of this easily. I would probably, when I'm approaching left and right, when I'm going to approach, let's try x equals like 2.999, and then just think about this logically. Sometimes you can use logic in a good way. So my denominator, this gives me a really small number close to 0 but negative, which then is going to give me negative infinity. Now I can start to wrap my head around this. I could write that as 1 over 2 to the infinite power. 2 to the infinite power is infinity. 1 over infinity is 0. So this will actually approach 0. So hopefully that makes sense. Those are just some limit examples. So I'm going to stop the video there, and then we'll pick up. We will pick up here in the sense of what we've kind of done. A number of things, and I'll show that in the next video. Is we've just now shown that the derivative of this is e to the x. We've proven that. And then the next video we'll go through where those come from and what they are and take derivatives of them and limits. All right.